Alright, if I did not get your section 1.9 worksheet, which was number 80 in your binder in Google Classroom, you need to come turn that in hard copy and put up your phones and smartwatches to the front of the board, please. You're welcome to use the calculator if you want, but I don't know that the calculator is going to help you.
Please stand as you are able for the pledge. Allegiance to the flag of the United States of America, and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Have a great day.
Alright, so again, sorry I got cut off there. If you think a calculator would help you on a question, feel free to use it, but it's going to do very little, if anything. let's move on here. So there's two new handouts that you guys picked up. Both of these are over section 3.1. So again, as far as the textbook numbers go, it's kind of a jump. Inverse stuff was in 1.9, but really that was just to help build us towards logarithms, which we're still moving there. So section 3.1 will be over exponential, but then 3.2, 3.3, and 3.4 will all be logarithms. So that'll be what we do all before spring break and a little bit after spring break. ACTM reminder, if you are interested in signing up for that, again, that's a math competition, math test, Saturday, March 3rd, March 4th. I don't remember which one it was, whichever one's the Saturday at 10 in the morning. There's quite a few of you that have shown interest in doing that through Mu Alpha Theta, because I know they're giving you like some tutoring hours to do that. However, you are not officially signed up until you pay the $5. So if you're interested in doing that, that is great, but I need your $5 by Friday at lunch. So realistically, you should try to bring it to me tomorrow. That way, if you forget, you could bring it to me Friday during class. But if we don't have your money, then we can't turn over your name to be signed up. So please make sure that you're doing that if that's important to you. Okay, so we're going to go over all of the notes together, which is number 82. And then number 83 has a front and the back that's the same. So I'm going to do the front with that, or front with you, and then the back is going to be your practice homework. But you should have very little of it to do outside of class. But first off, 82. So we need to talk about what an exponential function is, a couple application questions, review a little bit of exponent rules, all the stuff that's going to kind of come up in this section. So first off, we need to know what an exponential function is, and that is a function where the variable is up in the exponent. So like 2 to the x, 3 to the x, the variable is in the exponent. That's what makes them exponential functions. Now, you really kind of want to know what these two look like very quickly, but for our first time at looking at them, which is of course true for all graphs, you don't know what it looks like, just plug in a few points. Let's plug in 0 for x. What is 2 to the 0 power? 1. Very good, it's 1. Anything to the 0 power is going to be 1. That's going to come up a whole lot the next few weeks. And we could plug in 1 to get 2, plug in 2 to get 4, plug in 3 to get 8. So we kind of know what the right side of the graph looks like. And then if we did the left side, or some of the left side, maybe like -1, 2 to the -1, and we're going to talk about this on the next page. If you have a negative exponent in the numerator, you should move it to the denominator to make it have a positive exponent. So 2 to the -1 is the same thing as 1/2. And of course you can plot points all day, but that is what 2 to the x ends up looking like. Exponential growth is growth because this value under x is bigger than 1, so that just means the graph grows exponentially. Each step you take, it rises very, very quickly. Okay, and then if we did the same thing for 3 to the x, again, if we just assume we don't know what it looks like, we can plug in a couple points. 3 to the 0 is 1 because anything to the 0 power is 1. Maybe plug in 1, maybe plug in 2. What do you think 3 to the -1 is going to be?
1/2.
Good, it'll be 1/3. Same reason as this. A negative exponent in the numerator is the same as a positive exponent in the denominator. And you can also just plot points all day, but that's where it kind of helps to know what the graph looks like. So, two things I want you to get out of these first examples. One is, because this is 2 to the x, 3 to the x, these numbers are bigger than 1. That's why the graph looks like an exponential growth. And two, and maybe more importantly, you need to see that these graphs are basically the same thing. The graph of 2 to the x, the graph of 3 to the x, the graph of e to the x, 5 to the x, 10 to the x, they're all basically going to look the same. Now, some of them are going to rise a little bit quicker, some of them are going to hug to this x-axis a little bit quicker, but the general shape of an exponential growth is always going to look like that. So that'll be helpful to us later. Now, if this number under the x, the base is less than 1, this is what we call it exponential decay. And you could do the same thing, but 2 to the x and 1/2 to the x. We'll talk about y with exponent rules in a minute. But this is really just a y-axis rotation. Or y-axis reflection. Exponential decays go down over time. They decrease. So again, 1/2 to the x, 1/3 to the x, 1/5 to the x, 1/10 to the x. All of those graphs are basically going to look the same. The points are going to be slightly different, but the overall shape and direction of the graph is going to be the same. Now, of course, we're going to work with more interesting functions than that, but most of what we need that is going to be more complex than that is to just review the transformation rules. So, same transformation rules that we used in first semester, the same transformation rules you learned in Algebra 2, but if you just add a number to the outside, it's going to shift the whole graph up that much. You subtract a number from the outside, it's going to shift the whole graph down that much. The two that are not real intuitive, if you add to x, it goes left that much, and if you subtract from x, it goes right that much. If you multiply your whole function by a negative, that's how you get it to flip over the x-axis. And then number 9, this is one that you guys don't remember much, partly because you just don't see it as often. But if you just multiply x by a negative, not the whole thing, that's how you flip it over the y-axis. So I'm not saying anything new with their transformation rules there, but just in case you've forgotten any of those, I want you to have them written down. Okay, anything that jumps out at you at page 1 that you'd like to get some clarification on? Okay. Then most of page 2 is already filled out, so it's kind of some stuff I already pointed out to you, but here's an example of an exponential growth on the left. Here's an exponential decay on the right. And then notice, these are just y-axis reflections here because of exponent rules, 2 to the x and 2 to the negative x. If you're only multiplying x by a negative, that's how you flip something over the y-axis. That's why those graphs look the same. But within the graphs, we're going to ask you some stuff, all of these type of things. And in my opinion, if you know what these things are asking for and you can get the graph correctly, then you should be in good shape. So just like we've done several times this year, domain is asking what x values does the graph hit. Looks like it goes forever left and forever right. Forever left and forever right. Range is asking what y values does the graph hit. It goes as low as 0 and up forever, as low as 0 and up forever. That's why the range is that. Y-intercept, both 0, 1. This graph is increasing because it goes up over time, and this graph is decreasing because it goes down over time. And a graph, you should always read left to right like you do a book. If it's going up left to right, it's increasing. If it's going down, it's decreasing. Now, it's almost tempting to say there's a vertical asymptote here and here, but these actually do keep going to the right. It's just very slow because it's going up so fast. So there is no vertical asymptote. But both of these have a horizontal asymptote because the further left you go, the closer y gets to 0, and the further right you go, the closer y gets to 0. So that is why there is a horizontal asymptote at y equals 0. So when we get to worksheet 1, we'll graph something with some transformations, and we will answer the same type of things about the graph. So mostly you just need to know what to look for. Okay, and of course, if we are doing exponential functions, we're going to need to remember some exponent rules. So let's go ahead and I want to verbalize all of these to you and maybe throw out a few examples, but the main thing you need to do is just mark the couple that you feel less comfortable with. So you've seen all of these before, but some of them you just don't use very often. So I've said this one a few times already today, and I'll say a lot for the next few weeks. Anything to the 0 power is 1. Also on the front page, we talked about how to deal with the negative exponent. A negative exponent in the numerator is the same as a positive exponent in the denominator. A negative exponent in the denominator is the same thing as a positive exponent in the numerator. And then there's just one more example. So those are all saying the same thing, really, how to deal with negative exponents. This one is one that you should feel super familiar with. Just like x times x is x squared. And the reason why it works that way is if you multiply things with the same base, you add the exponents. So if you divide things with the same base, you subtract the exponents. You sometimes think of this as like 2 of these x's cancel out 2 of these x's, but you can also think of it as subtracting the exponents, 3 minus 2. If you raise a power to a power, they get multiplied. So if I showed you like x cubed squared, because that's squared, it means you've got 2 of them. And x to the third times x to the third would be x to the 6th. So in the end, you just multiplied the exponents. If you raise a bunch of stuff to a power, then everything gets raised to that power. The m and the y here both get raised to the m. And then another example, if this stuff is all raised to the third, 2 gets raised to the third, and x gets raised to the third. So again, I would just suggest that you put a star by the 2 or 3 that you feel less comfortable with, so that if you need to look back at this, you have a quick, or it's quicker to review it. But all of these things will show up here and there today and Friday. Okay, and to be truthful with you, exponential functions and even logarithmic functions, most of the real world applications that go along with those just don't show up much until higher science courses. So you may have done some stuff that just fits, you know, like bacteria spreading, growing, that type of stuff. You may have done some basics like that, but most of the real world applications for these type of problems will show up for you in science courses. But we, at least with exponential functions, there's 2 types that we would like you to do. One of them is the compound interest formulas, partly because you should have learned this in Algebra 2, and also it used to be big on the ACT. I don't know if it still is, but it used to always be on there. And working with some half-life formula stuff. So I don't know any science stuff, but I'll show you why it doesn't matter, and you can still answer these question types. So for the compound interest formulas, you do have to memorize these 2 and when to use them. The PERT formula is if you compound continuously. And the other formula, sometimes students call this the print formula, I guess because like it looks like the word print, maybe a little bit scrambled up, is for if you compounded a certain number of times per year, n times per year. But both of these formulas have a lot in common. Both of them have a P, so you need to know that P stands for principal or starting amount. So that could be like how much of a loan you take out or how much of an investment you make. Just however much it's starting with is what we plug in for P. Both of these formulas have an R, which stands for the rate, and you need this always as a decimal. So if something was 50%, you should not put 50 in place of R. You should put 0.50. Always needs to be put in as a decimal. Both of these formulas have a T, which is for time in years. So if it was only 6 months, then T would be 1/2. And then the other 2 things depends on which formula you're talking about. If you're compounding continuously, you've got an E in here. This E is just a number, just like pi is just a number. E is about 2.718, about. In our calculator, second divide is how we access that. It's this lowercase e, not the uppercase e. Uppercase e is like if you're typing out a message on your calculator. Second divide pulls up the e that we need, and that just shows up naturally in quite a few different places. So we need to know of its existence. And then the other formula has n, and n is for number of times it compounds in a year. So if the question says it compounds annually, annually means once a year, and you would plug in 1 for n. If it said quarterly, quarterly is 4 times, so you'd plug in 4 for n. Monthly, you'd plug in 12 for n. Daily, you'd plug in 365 for n, just however many times it gets compounded. Now, when we do worksheet 1, we'll do an example where we have some numbers and make sure that we plug those in correctly. And I don't want to take too long on this because I do want you to mostly finish worksheet 2 in class so that you have very little homework. However, I do want to take a minute and kind of talk about this one, because even if somehow, if you guys decide not to pursue a career in math or science, this formula is probably the one that's going to impact your life the most, because this is the formula that banks are going to use. And so someday you're going to want to buy a house, and you're going to go to them, and you're going to need to borrow some money. So that's going to be the principal. So what do you think the average house value is in Fayetteville? 250. I think that might be a little high, but that's probably not too far. Of course, everything's been going up lately, so maybe that's true. So, by the way, if you want to buy a $250,000 house and you go to the bank and say, give me $250,000, they're going to say no. You have to have like some of the money up front to show that you're going to do it. But let's say that you borrow $250,000. And I believe they go with the compounded continuously because it's just a tiny bit more money. The rate, now, I bought my house a while back and it was 4.25, and then the rates went down and then the rates went up. But I think someone in my last class was pretty sure that it was 6.25% right now. So I'm not 100% sure on that, but that fluctuates. But if it is 6.25%, again, that has to be typed in as a decimal. What about how many years? How many years do you have to make payments on your house before you own it?
30.
Very good, 30. A standard mortgage is 30 years. So, if you go to the bank someday and say, hey, can I have $250,000 to buy this house? And they look up the interest rates and it's 6.25, and you want a standard mortgage of 30 years, by the time your 30 years are over, you will have paid them back $1.6 million. That's a lot of money. So, one thing that you can do, why this is important to you, is if you want to buy that house, I don't know, you can save up more money so you have to borrow less. Same house, but let's say you saved up an extra $50,000. Well, saving $50,000 up front ends up saving you like what? $300,000, $330,000 over 30 years. So that's a lot of money. I mean, that's a good chunk of your work life that's going to be paying towards that. But also, they will let you do a 15-year mortgage. So what do you think the difference is with the 15-year mortgage? Okay, it'll be less for sure. But what would be tough about a 15-year mortgage versus a 30-year mortgage? Yeah, you basically have to make 2 house payments a month instead of 1 house payment a month. But if somehow you can budget that in, instead of paying $1.6 million over 30 years, you're giving back about $640,000. So, if you can somehow financially make that happen, then you're saving yourself a ton of money. Likewise, you may have heard the saying before that it's expensive to be poor. Well, this is why they say that kind of stuff. Because if you have a lot of money, if you have $250,000, you go and buy the house, you give them your $250,000, and that's what it cost you. But if you don't have that, and your money's tight, you spread it out too thin, then overall you're going to be given a $1.6 million over 30 years. And if you have a little bit more money and you can afford to make 2 house payments roughly a month instead of 1, then you only end up giving them 638 for that 250. So definitely, and cars are the same way. Of course, cars you're borrowing a lot less and it's for a lot less time, but when you guys make those kind of commitments, like that dictates a lot of your work life and what you're building towards. So, you know, of course you want the nice big house and stuff, but it's a big argument for having to borrow a lot less and just taking what you need. Okay, and finally, the last type is going to be half-life, and there is a bunch typed up here that you can read through. I don't know that this is really needed. I think it'll make more sense when we look at an actual example. But half-life means, like, if you start off with a certain amount of something, like 60 grams, how much time has to pass before it's half of that, 30 grams. So that amount of time is something that we can solve for pretty realistically. Okay, so move on. The other handout we've got is worksheet 1 and 2. So worksheet 1, I'm going to go over all of this with you except for part A. We're going to do that next class. So you will be responsible for coming back and finishing this part A. Every year there's a few students who don't do it and then get half credit on their work, and they say, well, I thought we didn't have to do that one. That's true, you don't have to do it today because we're going to focus on the other stuff, but you do need to come back and do it, and I will tell you that on Friday. But otherwise, the rest of the questions are the same, front and back, so I'm going to do the front with you and then give you a chance to try the back. So question 1 has a million questions about this function, and we need to do this without a calculator. So if I want to answer things like domain, range, asymptotes, increasing, decreasing, what are some points, all that kind of stuff, I really kind of need to know what this looks like. So what I would suggest to you, what seems to work the best for students, is start off with the parent function. In all of this mess, we've got 3 to the x, and we talked about why 3 to the x looks roughly like this. We're just doing a quick sketch. Then think about if you plug a number into x, the first thing you would do is add this 1 to it. So you need to think about what transformation that is, and that would be shifting it left 1. So try to make your graph look like it goes left 1. The next transformation would be dealing with this negative, and this negative out front like this flips your graph over the x-axis. So now it looks roughly like that. And then finally the -1 is going to shift our whole graph down 1. So I'm going to take this and do my best to make it look like it goes down 1. Even as quick and as rough of a sketch as that is going to help me with most of these questions. So know the parent function, know your transformation rules, sketch them out, and then let's see what we can answer. So domain's asking what x values does the graph hit? Well, he goes forever to the left and he goes slowly to the right, but he does keep going to the right. So he has all the x values. Range is supposed to describe the y values. So I see that he goes down forever, but then he goes up, and then it looks like he kind of flats right here. Now, admittedly, my graph is not very accurate, so it's hard for me to know what y value he's approaching. But that's where these would be helpful still. The range of this was 0 to infinity. If I shifted it left 1, it's still 0 to infinity. As soon as I flipped it over the x-axis, now it's negative infinity to 0, and then I shifted it down 1. So now it's negative infinity to -1. So even though it's not super accurate, I can still keep up with the range step by step and figure that out fairly easily. Okay, these do have a horizontal asymptote, so it was at y equals 0. Left 1 is still at y equals 0. Flip it over the x-axis, it's still at y equals 0. But then we went down 1, so now it's at y equals -1. -1 is the y value that it approaches on the far left. This sort of looks like an asymptote, but again, it does drift. You do keep going, so there is no vertical asymptotes on these. When we do logarithm graphs, it'll be opposite. They won't have horizontal asymptotes, but they will have vertical asymptotes. Over time, my graph is going down, so we call that decreasing. Concave up, concave down. My last period said that they did not hear those terms in Algebra 2, but that's okay. It's just the shape of the graph. This is very big in calculus, by the way. We do lots of work to figure out what's called the concavity of a graph. But concave upward just means the graph opens upwards. So this is concave up, this is concave up, but this is concave down. This is concave down. Okay, if I would like to know the point when x equals 1, I guess I can look at my graph, and when x equals 1, I can tell it is something negative, but my graph is so much of a sketch that I don't want to guess that. So, like with any function in algebra, if you want to know the y value for this x value, just plug it in and solve. There's no reason to guess. When x is 1, y is negative 10. H sounds different, but it's really the same thing. Instead of saying when x is 1, it's saying y-intercept, which is when x is 0. So you can plug in 0 for x and solve, and you get negative 4. Now, referring back to my quick little sketch here, if 1 negative 10 doesn't look realistic, if 0 negative 4 doesn't realistic, then I would be questioning, did I do this correctly? Because I know those should be points on the graph for sure. So that might give you an indication that something was off. It also asks about the transformations, but I already did that. I started with this, realized that first it should go left 1, so I sketched that. Second, I realized that he was reflected over x-axis, so I did that. And then the last transformation I did was to shift it down 1. So I've already thought about it, I just didn't write it in words. J is not one you need to worry too much about, although I do want you to fill it in and fill it in on the back where it asks you the same thing. These are sometimes called transcendental functions. The only time I think you might ever see that word in high school is if you compared a bunch of different calculus books. Some calculus books do early transcendental functions, which means they do calculus with these type of functions early in the book, and some do late transcendental functions, so some just choose to deal with them later. So just a difference in philosophy. I'm not really sure why that's on here, but again, I do want you to go ahead and put it down. Alright, K. Use all of the information from A through H to give a detailed sketch of what we had. Well, this is actually going to be really easy because we've done a lot of the legwork. We've got 2 points. We can put them both on the graph. And we know the horizontal asymptote that it approaches. Asymptotes should show up as dashed lines. And really the only other thing that we kind of need here, I mean, you can always put in more points. More points is always better. That's what your calculator does. Your calculator just graphs hundreds of points and then makes it look like a line. But up here, we knew what the general shape of the graph looks like. So I know that these are going to connect like this, and this is going to hug up next to the asymptote like that. That's already a pretty detailed graph. And it's consistent with everything else we said about domain and range and all that other stuff. Okay, we just talked about what it means to be one-to-one. It's got to pass the vertical line test and horizontal line test. Hopefully you remembered that for today's quiz. This does pass both of those. Even though this looks like horizontal, it is technically just tiny bit going up all the time. So he is one-to-one. Oh, did I talk about Euler's number in your notes? I think I missed that. Sorry, I must have moved on too quickly. Yeah, I did. So this is another one that we're not going to put this on the quiz or anything, but it's good for you to know that the number E, that's 2.718, is not just some number that someone decided, let's make this number important. Just like pi is the circumference divided by the diameter, any circle you take, if you take a circumference length divided by its diameter length, you always get pi, so it just naturally occurs a lot. The number E comes from this and as you make these x values bigger and bigger and bigger, E gets closer and closer to what it actually is. So again, because it just naturally occurs with a lot of stuff that we do, we end up using it a lot, but it's not man defined. It's this ratio that just happens to occur a lot. So let's go ahead and copy that over. Again, you don't need to feel like you need to memorize that or anything for our quiz, but I do expect you to at least fill it out for your homework. Okay, part A is what we will look at some on Friday. We're going to do that and a couple other commonly missed question types on Friday to finish up section 3.1. And then finally for worksheet 1 here are two different type of application questions that we're going to ask you to do. So first off, if you are asked to compound continuously versus not continuously, you have to know PERT is the continuous one and print, if you want to call it, is the non-continuous one. You'd have to have those two memorized. Since they gave us a starting amount of 2,000, that would go in place of P. Regardless of which formula you were using. I think it's 2,000, yeah. Both of these ask you to put in the rate, but it needs to be put in as a decimal, so don't put 6.5 in place of R, put 0.065. Both of these require you to put in the number of years for T, 30 years, 30 years. But what is different about them, if it's continuous, it's going to have this number E in the formula. And if it's not continuous, it's going to have this number N, where N is how many times a year it would get compounded. And if you want it to be compounded daily, then N would be 365. So these formulas work whether it's talking about a loan and you're borrowing money and how much you're going to have to pay back, but also if you invested money. So I think it would be hard for you to find a place that would give you 6.5%, but if you had $2,000 and you found that place and you could leave your money alone for 30 years, after 30 years it would be about $14,000. If it was compounded daily instead of continuously, it gets put in the calculator a little bit differently. But honestly, daily and continuously are pretty close to the same thing. So 14,000, 54, and 93. So whether you were compounding continuously or daily, you're talking about less than $3 difference over 30 years. So you're not going to be worried about that. But now, in the past, we have made this no calculator sometimes. So typically when we do no calculators, we would make this multiple choice and you would just pick out the answer that looks like this or looks like this. But it's good for you to practice throwing it in the calculator in case we give you a calculator. So you will have to memorize those formulas. If you don't remember them, you have to know what P, R, N, T are so that you plug them in, and then as long as you can plug them in the calculator correctly, then you should be fine. Okay, and then the last type, which was the half-life type thing. So we've got a radioactive isotope, and how much mass it has is given by this formula. And again, I know next to nothing about chemistry, I took a bunch of biology courses, biology, microbiology, stuff like that in college, and physics courses, but you don't need to know any of that kind of stuff because of the questions that we would ask you. So the first question is, how much mass did you start off with? Initial mass is when time equals 0. So if we plug in 0 for t, we can solve this because 0 divided by anything is 0. What's 1/2 to the 0 power? One more time. 1, because anything to the 0 power is 1. So you're starting off with 40 grams. When t is 0, the initial time, we can just plug that in and solve. The other question we might ask is how many years have to pass before it reaches half of his initial mass? So again, this is what's called half-life. So if this formula tells me how much mass it has, and he's starting off with 40 grams, when he gets to 20 grams is his half-life. So I'm setting it equal to 20. Now, to be honest with you, most of the time you're solving for a variable in the exponent. We're going to have to deal with and work with logarithms, but we haven't reviewed that yet, so these questions have been set up to where we don't have to do that. We could start off by dividing both sides by 40. And then what happens is you get 1/2, that's to the first power, is equal to 1/2, that's to the t over 2007. So to make these equal, all we got to really do is make the exponents equal. So in that case, it would be 2007 years. And I think that's really not that far off from being realistic. Radioactive stuff takes a long time to go away. So for 40 grams of radioactive material, to get it to decay down to 20, you'd have to wait over 2,000 years. It takes a long time. So again, you don't really need logarithms here. You don't need to know anything about chemistry or anything like that, but those are the two ways that we would ask you to try to approach that. So what I'd like you guys to do is try without a calculator, review 2, which is on the back. So it's got a different function here, but similar questions. Again, skip part O on the back until we talk about that on Friday. But then make sure you can set up the interest formulas. Actually try a half-life question on your own. And you guys have about 17 minutes of class. So do your best to try to finish that while you're here. But if you do need to spend a few minutes to finish it up, then please do. And I should have the answers on my website, so at some point check your answers to make sure they're right and not that you're just assuming that they're right. Obviously, if anything pops up that you guys want to ask about, then please do.